It's kind of crazy when you think about it. There's this invisible force powering literally everything around us. The screen you're looking at, the lights in your room, everything. But what is it really? Well, that's what we're going to unpack today. Let's get into the fundamentals of electric current. So what is this spark? What's the secret sauce that powers our world? It all comes down to the movement of these incredibly tiny, tiny particles. You see, it helps to stop thinking of electricity as a thing and start thinking of it as a process, a flow. And that idea of a flow is the perfect starting point. So let's talk about the flow of charge. I want you to try something. Picture an invisible river. Seriously, flowing through all the wires in your house. That river, that's electric current. All right, so if we're going to get a little more textbook about it, here's the official definition. Electric current is simply the rate of flow of electric charge through a conductor. The keywords there are rate of flow. It's not just that charge is moving, it's about how much charge is moving past a point in a certain amount of time. And of course, we've got a formula for that. It looks simple, but it's super powerful. I equals dq over dt. So I is our symbol for current, and it's just the amount of charge, that's the dq, that flows over a period of time, that's the dt. We measure all this in amps, or what you'll usually hear called amps. Okay, now here's where things get weird and kind of interesting. There are actually two ways to look at the direction of this flow. See, way back in the day, scientists like Ben Franklin had to guess. They figured it was positive charges moving, so they said current flows from the positive terminal to the negative one. We still call that conventional current. But they guessed wrong. We know now it's actually the negative electrons doing all the work, flowing from negative to positive. The math works out either way, but you absolutely have to know which convention you're using when you look at a circuit diagram. It's a huge deal. So if you could zoom in and follow a single electron, its journey isn't this smooth, straight line. No way. It's more like a chaotic pinball machine bouncing all over the place. But when you apply an electric field, like flipping a switch, they all start to slowly kind of drift in the same general direction. That average speed is what we call drift velocity. The formula for it's a bit more involved, as you can see, but the big idea is that this slow collective shuffle is what actually creates the current we can measure. All right, so we've got this flow of electrons, but how does that relate to everything else happening in a circuit? Well, that brings us to what is, without a doubt, the golden rule of all electric circuits. We're talking about Ohm's law. And there it is. So simple, so elegant. V equals I times R. Voltage equals current times resistance. If you remember one thing from all of this, make it this formula. It is the absolute bedrock of circuit analysis. Seriously, burn this one into your brain. Let's break that down so it really sticks. Think of V, voltage, as the push, it's the pressure. I, the current, is the actual flow itself. And R, resistance, is the opposition. It's whatever is trying to slow that flow down. The water pipe analogy is just perfect for this. Voltage is the water pressure. Current is how much water is actually flowing, and resistance is like squeezing the pipe, making it narrower. So does everything in the universe just blindly obey this law? Not exactly. You've got what we call ohmic materials. Think of a standard resistor. For them, the resistance stays constant. They follow V equals IR perfectly, no questions asked. But then you have non-ohmic materials. Things like the filament in an old-school light bulb or a diode. Their resistance actually changes depending on things like temperature, so their relationship isn't a nice, clean, straight line. And since we're on the topic of resistance, let's dig into that a little deeper. Because once you understand resistance, you understand how we can actually control the flow of electricity and build useful circuits. So what is it that makes a wire resist current in the first place? Well, it really comes down to three main things, all right here in this formula. First, you've got rho, that little Greek letter, which stands for resistivity. Basically, what's the wire made of? Then you have L for its length, and A for its cross-sectional area, or how thick it is. Let's take length first. It's pretty intuitive, right? Imagine you're an electron trying to run a race down a wire. The longer the wire, the longer the race. You're going to bump into more stuff. It's just a harder journey. So, simple rule. Longer wire, more resistance. Now, what about the thickness? Well, making a wire thicker is like turning a one-lane country road into a 6-lane superhighway. Suddenly, there's a ton more room for all the electrons to flow without bumping into each other. You get way fewer traffic jams. So the opposite is true here. thicker wire less resistance. Okay, so the wire itself has resistance, but how we arrange components in a circuit also makes a huge difference. First up, we have series circuits. That's when you line everything up in a single path. To get the total resistance, you just add them up. And the key thing to remember for series is that the current is the same through every single component. On the other hand, you have parallel circuits. This is where you give the current multiple paths to take. And this is cool. It actually lowers the total resistance. For parallel, the big takeaway is that the voltage across each path is the same. All right, we've tackled current, voltage, and resistance. Let's add the last piece of the puzzle, power. That's basically the rate at which we're using energy. And after that, we're going to put your new knowledge to the test with a few quick practice questions. You ready? Electrical power, which we measure in watts, is super important. We call this the power triangle. The most basic one is P equals V times I. Power is voltage times current. But using our good friend Ohm's law, we can swap things around and get two other super useful versions. P equals I squared R and P equals V squared over R. Memorizing all three will save you a ton of time. Okay, let's do this. Time for a quick knowledge check. We'll start with the very first thing we talked about. If you have 3 coulombs of charge flowing past a point in a wire and it takes 2 seconds, what's the current? Go on. Think back to that first formula. And the answer is 1.5 amps. If you got that, awesome. Remember, current is just charge divided by time. So 3 divided by 2 gives you 1.5. Perfect. All right, next one is less about the math and more about the concept. Let's say you take 2 identical light bulbs and you wire them up in series. That's one right after the other. Are those bulbs going to be brighter or are they going to be dimmer than just having a single bulb? The answer is they get dimmer. But why? Well, remember what happens in a series circuit. You add the resistances. So 2 bulbs have double the resistance of 1. Now, think about Ohm's law. If the voltage from your battery stays the same, but the total resistance goes up, the current has to go down. And less current means less power, which means less light. It all connects. And for our last one, let's circle all the way back to the beginning. It's a review question. When we're drawing our circuit diagrams, what is the direction of conventional current? You got it. From the positive terminal, through the circuit, and back to the negative terminal. It's so important to remember that this is the standard convention we all agree to use, even though we know deep down those pesky electrons are actually going the other way. And there you have it. We've gone through the absolute essentials. What current is, the golden rule, that is Ohm's law, and how circuits work. The most amazing thing is that everything, from the tiny chip in your phone to the massive power grids that light up our cities, is built on these few, simple, elegant laws. So the question I want to leave you with is this. Now that you know the rules of the flow, how do these simple principles combine to power our entire complex world?